Hello and welcome everybody to the live session 2.1 of PQCrypto 2020. So this session is going to be an invited talk from Professor Frank Wilhelm-Mauch on the current state of affairs on quantum computing, which I think it's a very interesting and hot topic, especially for the PQCrypto community. So before starting, a few details. We have a Mattermost channel, so you can ask questions on the channel 2.1 of the PQCrypto 2020 Mattermost. We will try to keep the speaking time around 50 minutes, so there might be time for a few questions at the end. So without further wait, it is my pleasure to introduce the invited speaker for this session. Professor Frank Wilhelm studied physics at the University of Karlsruhe in Germany, where he obtained his PhD in 1999 with a thesis on condensed matter theory. He started working on quantum computing in 1999 at TU Delft in the Netherlands, and in 2001 he moved to Munich, where he was appointed lecturer in 2004. In 2006, he joined the University of Waterloo, Canada, as an associate professor at the Institute for Quantum Computing, with a cross-appointment to electrical and computer engineering, where he was promoted to full professor in 2011. He became a full chair professor at Saarland University in Germany in 2011. And as of July 2020, he is the founding director of the Institute for Quantum Computing Analytics at the Research Center Jülich. So I leave now the speaking token to Professor Mauch. Let me switch to make presenter. Okay. And please go.
Thank you very much. Thanks a lot for having me at this great event. I think we are obviously scientific neighbors in the sense that my research I'm doing mostly theoretical research on hardware, but also more and more on its applications. And I think you all have an interest in the progress of quantum computing because you want to avoid some of its impact. So what I will assume that we have a mixed audience, that some of you are really mostly interested into quantum safe cryptography and have looked very little at quantum computing, and some of you may actually be reasonably familiar. So there will be some basics, where some of you may be slightly bored, and there will also be some extremely recent developments. This work is based on my own research experience in the quantum technology flagship, but it's also based on a study that we wrote for the BSI, the German Information Security Office, where the 2020 update should be coming out right now, which is also written, which is publicly available, which is written in English, and which has given us the opportunity to really assemble a lot of information that we need to evaluate where things are kind of in one place. So if you listen to the big news and also the hype cycle about quantum technology, say around the flagship program of the European Union, let's keep in mind that people are typically discussing 4 pillars there: sensing and metrology, communication, computation, and simulation. Now, quantum communication is, for example, involving quantum key distribution. It's a way to use quantum physics to make secure communication. This is not the topic of today's presentation. Today's presentation is centered around computation, around the progress of building quantum computers, but there will also be some connections to its neighbor, the field of quantum simulation, and I'll come to that. Now, here is in a nutshell, and slightly oversimplified, putting quantum and classical computers next to each other. Classical computer on the left, it's oversimplified, but hey, it has a tape, is using binary information. Any register in the classical computer at any given time has a well-defined binary value. Even if there's randomization, after a random number has been generated, the value of the register will be well-defined. And then you run commands on these registers one by one. So if you would like to run a parallelized algorithm, you need parallel hardware. You need some type of multiple cores. In a quantum computer, the information that you're interacting with is still binary. It's still consisting of zeros and ones. But now you can bring your registers into states like the one indicated here. I guess most of you will be familiar with quantum mechanical notation, but just to bring us to the same page, these cats, these half brackets, are state vectors. These strings sigma I are essentially strings of 0 and 1, and we are in principle summing all of them. And the coefficients C sub sigma I are complex numbers that need to obey some normalization condition, but are otherwise arbitrary. So in a way, a kind of fully general quantum state like this has components as a superposition of state vectors, of basis vectors, that refer to multiple binary values. And the prefactors are controlling the probability amplitude, which simply means you take the absolute value and square it and you get a probability. So in this state, in this sense, this state contains many, and in principle, all possible binary numbers at the same time. However, if you were to read out which one you have, you'd only get a probabilistic answer. So in this sense, quantum computing can be intrinsically parallel, or to show this in another way, is that a good quantum program takes binary input and binary output. You allow maybe for some ambiguity for the output value, but you certainly do not want to have a full superposition, which means a state vector where all of these C coefficients are non-zero. Physicists sometimes say finite when they mean non-zero. I try to avoid that. If all these coefficients are non-zero, then, and if we have in principle 2 to the n, where n is the length of the register possible values, then making a measurement, finding out which value we are in, would only give us a probabilistic answer that is exponentially thin. We do not want that. So a well-designed quantum algorithm starts with a binary output. It uses quantum parallelism in the middle, but in the end, it uncomputes some of the superposition and gets another binary output. With some reasonable success probability. It doesn't have to be 100%. Oops, how do I avoid my mouse from zooming here? Maybe by going back and forth. Now I have zoomed, sorry. Anybody have, here is the zoom button. Now we're at 100% again, and the hand symbol is also gone. Sorry about that, I'm getting used to this. So it would be, too simple to say that any parallel or parallelizable algorithm known to humankind can be accelerated like this. You really have to find these algorithms, you have to discover them, and this is hard, but there are known solutions, such as Shor's algorithm. And of course, there are some other applications that people are discussing about, like theoretical chemistry, material science, combinatorial optimization, machine learning, and so on, which are all reasonably fundamental. So parts of quantum computing research is to map these basic algorithms to applications. Now, this is kind of setting the stage, and most of you have seen these things, probably in more sophisticated form before. But for the rest of the talk, I want to talk to you about kind of 3 ways to building a quantum computer. One of them is called NISQ, or Noisy Intermediate Scale Quantum Computing. And I will also put a number of recent announcements and results in this field in context, and I will explain you what it is. Then I will explain how fault-tolerant quantum computing works and what to look for in this, and also recent progress. And if time permits, I talk a little bit about quantum annealing and adiabatic quantum computing. So here are the 3 paths. I've uploaded a PDF. Sometimes I have animations, but well, here we go. So what we call NISQ, or Noisy Intermediate Scale Quantum Computing, is here in the middle. You make a quantum processor. You ideally design it in such a way that it runs whatever you want to run appropriately. So you do some co-design of hardware and software. And you try to natively on the quantum computer run your algorithm. Here, people have gone beyond 50 qubits already, and they have shown, and I'll detail this more in the next slide, that they have outperformed classical supercomputers in a kind of an idiosyncratic application, namely simulating the quantum computer. And the number of gates, the algorithmic depth you run is limited by physical errors. And I will explain later in the talk why intrinsically physical errors are such a big deal in quantum computing. And people are discussing to reach quantum advantage with NISQ in areas where memory savings are important, where classic computers run out of memory. Then there's the universal fault-tolerant quantum computer, which we error correct with massive overhead, which can in principle run everything. And I'll tell you where we are in developing this. And if time permits, I'll talk about quantum annealers and adiabatic quantum computers, which have reached much larger sizes. But the question, what it really takes to reach quantum speed up is way more so. But there have been some recent announcement also related to cryptanalysis with quantum annealers. So when you think about NISQ, noisy intermediate state quantum computers, you should think about a very primitive computer. On the left is the picture of the first computer I've ever owned. And on the right is a picture of the CEO of the company that made it. This is a Sigler ZX81. It had 1 kilobyte of RAM. It had a number of kind of very clever solutions how to work with such limited hardware. For example, it was programmed using the BASIC programming language. It was the 80s after all. And every BASIC command was saved in the upper half of ASCII with just 1 byte. So you could write a lot of code because the ifs and thens and fors and nexts of BASIC all were 1 byte. And these type of tricks, these type of using the hardware restriction really cleverly is also something that in NISQ quantum computers one should typically do. A typical chip, which is actually a bit outdated, but it was one of the last chips where you could get a picture that shows quite a lot of detail of a NISQ quantum computer looks like this. This is made by UC Santa Barbara right before the team moved to Google. And what do you see here? So the first observation is you see something which has color, and in fact, this is a picture done under an optical microscope, not an electron microscope. So the structures here are not super small. We're talking about hundreds of microns. If we were in person, I would have a chip that I could pass around where these little objects up here, you can actually see with your bare eye. So you see these crosses, these are the qubits. The active element is somewhere down here. And they are next to each other. They are coupled by electrostatic interaction, so by static electricity. And they're coupled nearest neighbor, which is something that one needs to take into account when programming there. And here you see the drive lines, and here you see curly lines, which are used for measuring a state. So this is separate, and you already see that if I want to make a 2D grid of this, I will have to make crossings between those lines and other elements, because if I make a square, there will be qubits that are completely in the inside, which is an interesting engineering problem. Fast forward to 2019, same group, bigger chip. It's now all encapsulated, so there's nothing to see anymore. This is a chip with 53 active qubits. It's the famous Google Sycamore chip. So in principle, you can make quantum superpositions. Okay, here I've now called all binary numbers S. I have an Apple Magic Mouse, which seems to really like to zoom here. Let's see how this goes. So, which in principle, to describe this quantum state on a classic computer, you need to save 2 to the n complex numbers. And if n is above 50, you have a large number of complex numbers that actually is more than the RAM that you have on the currently largest supercomputers. Now, for this being a really quantum computer, it should not only contain a lot of quantum mechanical elements, it should also do something. It should perform a task that is sufficiently general, so you're not taking any shortcuts, and it gives a hint that you can essentially program it universally. It also needs to be really quantum. So the technical term, it needs to be coherent enough. It needs to have a low enough error rate of errors that take you from quantum to classical. Otherwise, it's not a quantum computer. And because it's so big, you need a way to certify that it has actually worked. So how did the Google team address that? So first of all, this is the layout. You see here in gray the crosses that I've shown you. This is now a drawing, not a picture anymore, but you still see the crosses are still there. There's adjustable couplers, so you can now switch the coupling on and off by essentially having a circuit element in the blue boxes that can change the coupling, which means that you can, if the coupling is low, the qubits do single qubit gates. If the coupling is high, they're making 2 qubit gates between nearest neighbors. It's still 2D, so most qubits have 4 nearest neighbors. So they had to bring in wires from top. It's a 9x6 grid, but 1 qubit was defective. It had a defect that means you couldn't use it. And fortunately, it was on the boundary. And all the measurement infrastructure and the lines are now here in this setup. I should say that the yield of having 54 qubits and 1 broken is actually a big achievement. This technology, which is based on superconducting materials, is not super new. It has been used before quantum computing, but pushing it to this level is a new thing. And also there's much less experience here than with this material than the semiconductor industry has. So just 1 not working is actually pretty good. Now, the errors that these operations have made are consistently low. Previous work has shown that in this platform, I should say superconducting material is actually not very rare. The material of choice here is aluminum, or if you are in the UK, aluminium. I hate this tendency to zoom. And in previous experiments on the same platform, the record was around 0.6%. And very similar numbers, measured in slightly different way, were reached on average here. So even though people went to a bigger chip, the numbers did not get worse, which means there was no big breakthrough in making the devices, but it was very, very disciplined engineering in making these qubits, which is also quite a masterpiece. So the algorithm that they have run looks random. So here time goes from left to right. These boxes are different single qubit gates, and these couplers are controlled Z gates that are made in order. So between each qubit, you go around its neighbors, and you always go green, light blue, dark blue, red, and you repeat this pattern. And in fact, this doesn't only look random, it is random. And it's random in the sense that it simulates an output, it produces an output distribution that is known from a field called quantum chaos, which is the quantum physics of classically chaotic system that has been shown to be classically hard to sample from. So there's no shortcut other than writing down the distribution with 2 to the 53 numbers. And to validate that this was correct, they used a technique called cross-entropy benchmarking, which is designed to handle errors really well and to only use a subset of low error data. And you see here that they use different benchmarking techniques, because out here they were not able to simulate the whole system on a supercomputer anymore, but they could do things like patch circuits, which is simulate 2 halves and then connect them by hand. But they could consistently show that the cross-entropy benchmarking fidelity, which is a measure that checks is a quantum model the most likely way to explain the output data compared to a classical model, has still checked out well. And you also see that in extrapolating the classical runtime, at some point, they ran into very large values, basically reflecting that memory swapping and swapping to a hard drive is now kicking in. So this is an extremely synthetic benchmark that is meant to make the quantum computer to look really good. And I think for this pioneering experiment, which is mostly a technological tour de force, an engineering tour de force, this is very valid. One should just understand that this is obviously not the end, it's kind of a goalpost. So if you want, this is often being compared to the Sputnik moment or the Wright-Bartos flight of quantum computing. And in fact, IBM has shown that you can do this a lot faster in fewer days. If you save things much more efficiently, you still have strong growth. However, the Wright brother analogy is probably quite fair because the first plane by the Wright brothers flew for 13 seconds, which probably paper airplanes can also accomplish. But it was a milestone in the history to flight with engine planes. So we should really view this as an important milestone that the community has set itself and that the Google team has mastered. And in fact, to just give you an idea about the engineering tour de force behind it, I should say that in physics, other in computer science, the publication habits are very different. First of all, we publish in journals and not so much in conferences. And secondly, we publish very short papers, which the Google paper is also, and this is the technical appendix, which explains a lot of technical details. And you see that calibration, but also the programming and the benchmarking, the cross-entropy benchmarking, and the comparison to classical algorithms occupy the bulk of the simulation. And in groups like mine, this appendix has been required reading. Now, let's think about where to go from here. How do we go from this very academic quantum supremacy to something that is more applied, or you could call it useless and useful? So quantum computing, the idea was formulated very early, and this is the reference that these most physicists showed by Richard Feynman, who was a very colorful figure. There's very few people who can say by golly and damn it, which would be stronger expletives now, in a paper. And he just recognizes that obviously quantum systems, say if you have n two-state quantum systems that you would like to simulate, occupy these 2 to the n complex numbers, which means it's really hard to simulate quantum systems for classical computers. And typically this is for memory reasons. So if we can harness this, we can make an advantage. And in fact, here is a small excursion, because this is an often cited example on what people are looking for here. So you've probably, because you are in a STEM field, you've probably been exposed to some chemistry into these diagrams in high school or early in your studies. This is a molecule, and here are iron and sulfur. And it turns out this is called ferredoxin. It turns out that this is a very important molecule in the process of making nitrogen-based fertilizer that seems to be going on in plants. And plants are a big miracle because they can take nitrogen from the air and make it biologically usable at room temperature, where human beings need the Haber-Bosch process, which needs an enormously high temperature and produces an enormous amount of CO2. And this is a part of the molecule, is a part where approximation techniques that physicists and theoretical chemists have developed fail. So this is a moonshot of quantum computer chemistry. And the reason why this is probably the earliest point for applied quantum supremacy is that the compilation overhead of simulating this quantum system, namely the chemical bond, on a controlled quantum system, namely the quantum processor, is acceptably low. You can also use this for materials. This is the lattice structure of a high temperature superconductor, which is also very resistant to other methods. And the way how these algorithms are implemented are aware of the fact that the error rates are still pretty high. You know, I showed you 0.5% error, which means 1 error every 200 operations. And I claimed that this was actually a good result within the current state of the art. And the idea of these modern algorithms is that you run a classical algorithm that only at one point runs a quantum subroutine, a bit like in a hybrid bike. And after you've run the quantum subroutine, you reset the quantum computer. That is an operation that has a very low error, and so the errors are ideally gone. And this is, for example, what is done in quantum computer chemistry, where you're starting with a quantum state that is a good guess based on something called Hartree-Fock theory. Then you write down a quantum circuit that contains a number of real parameters, typically some angles, theta 1 to theta n, and you compute a new quantum state for which you would need exponential memory on a classical computer. But then you measure a polynomial number of output variables which in chemistry are called many-body observables, you run it through a classical minimization algorithm that gives you low angles. So by this, you are actually getting quantum advantage because you do not have to store the complete quantum state of the molecule or something else. You only have to do a polynomial number of measurements. And this is quite an industrial effort to make this as efficient as possible. Now, there has been a proposal to actually do the same with factoring in 2018 called variational quantum factoring. So we try to factor a number, we try to solve m equals p times q by writing a cost function that has binary numbers m, p, and q represented in this way. And then the mk, which are 0 and 1, are encoded in quantum states. And you're looking, do I have what is the minimum? And does the minimum put the cost function to 0? Now, you see that the results in this paper are plotted as a function of noise rate. So it's checking how good is the result as a function of noise in small instances up to 7 digits. And you see it's doing quite well until it collapses. But this is all extremely heuristic. There is not an indication of quantum speed up in the heuristic data, let alone a proof. So this paper shows that in these NISQ algorithms, you can do some factoring, but just because it's a quantum computer doesn't mean that there's any speed up. Now, let me also, of the state of NISQ, make a few other comments, because there were kind of landmark papers this summer. One is about quantum volume. This is a benchmark introduced by IBM that essentially runs square circuits. So circuits where the number of qubit and the depth, so the number of 2 qubit gates you're running is the same. And it's looking for an accessible success rate for 1/3. And they, by a lot of engineering, they improved their own record to a number that is 64 that you have to view in context. But the interesting thing is that they did not use their flagship chip with more than 50 qubits. They used the 27 qubit chip. And in this, they only used 6 qubits, clearly showing that by this non-artificial, more realistic benchmark, you're actually not using the full processor, you're only using a small subset. And Google has done something very similar. They looked at a chain of hydrogen atoms, and they were running a quantum chemistry simulation. It was reasonably sophisticated. All you need to take away from this chemistry plot with these funky units is that the quantum computer's data are really close to what you expect on a classical computer. And here they show that they are far away from the blue line, which means that they can actually distinguish different shapes of the molecule. So this means they're good enough for the simulation, but it's not the disruption because, hey, they could compare to a classical simulation. And for this, they used 12 qubits out of a 53 qubit chip. So very clearly, the performance of these devices is limited not by qubit number, but by errors. So we get the best performance on these medium-sized chips of 6 to 12 qubits. We are error limited. We are not limited by the number of qubits, and we need to work with the next step of the community should be to lower errors consistently. So my own speculation, this is a crystal ball from Wikipedia, is that the community will kind of say 50 is the new 2. So hardware researchers need to show that they can go to the 50 qubit level because this shows you some skill in running a real computer, not a physics experiment. But where 2 was what we've done 10 years ago. But I think we will stay there for quite a while because we need to really lower errors in this level before it makes sense to moving on. So in NISQ, I've, as outlined, the length of algorithms is essentially set by 1 over the error rate measured in appropriate units. It is built on algorithms that would be classically memory limited, and chemistry is probably the main application. So it's probably restricted to the simulation of other quantum systems. So how do we go longer? Well, we use fault tolerance. So let me comment on classical versus quantum errors. So there are clearly 2 reasons why we talk about quantum errors a lot more than we ever talk about hardware errors in classical computers. Remember that, so you are much better experts in classical computers than I am, but to my understanding, active error correction in classical computing, communication, clearly we need error correction in many cases, but in classical computing is mostly done in high security applications. In most other cases, we can assume that software errors kick in before hardware errors kick in, so we just tolerate them. And the reason for this is that if we have some energy that tells us here is 0, here is 1, this could be the energy landscape in a transistor circuit, then if we're just to the left of a dividing line, we call this 0, we call that 1. So typically the system self-stabilizes in this minimum, and only if we have an error that kicks us all the way over the barrier, we have a real physical error. And there is a formula called the Arrhenius formula that tells us if we make the barrier high enough, higher than room temperature, then this is exponentially suppressed. In quantum, it's different because we want to make superpositions of 0 and 1, and the prefactors matter. These are prefactors that are complex coefficients that we need to take into account all the way to readout. So while we run, we don't need precise numbers. We need just a low error rate at output, but the errors can accumulate over time rather than self-correct. And also because these are complex numbers, there's no bit and phase flip errors. So these errors have some analog character in it, even though quantum information is fundamentally binary. How do we deal with them? Well, we still take a playbook of something out of playbook of classic computer science. Similar to communication, we use redundancy. We compare bits to identify where the error happened. And this is reliable if the errors are sufficiently uncorrelated. And the more redundancy we have, the more protection we get. Now, there's an important aspect related to quantum measurement. Quantum measurement destroys quantum information. If I have probability amplitudes here and I measure 0 and 1, then the probability is gone. Then I know that I'm in 0 or 1 with certainty. So the superposition character, which is part of the quantum speedup, is disappearing. So we don't want that. We always want to detect the error without reading out the register. At the same time, what is nice is if we have an error that appears with some probability amplitude, then measuring it takes away the random character and it digitizes the error. So it helps us to keep the analog errors under control. Simple example, if I have a register in 0, 0, of course, for read error correction, I need an odd number of qubits, and I have a little unitary error that goes from 0, 0 to a state that has some amplitude in 0, 1. I can measure the observable ZZ, which is simply the product of those numbers. If this comes out to be +1, which it does with probability cosine squared theta, then I know I can keep the state. And then I have actually projected the quantum state onto this. If it comes in on -1, then I know I've made an error and I need to flip the second qubit. So the detection of errors makes the error digital. It gives you information where the error occurred. But a measurement of the product of 0 and 1 would not tell you has the error occurred in the first and second qubit. And this is kind of a technique in error correction, which is a vast field on its own. And here is the mainstream opinion on how this should be done, or what is one of the most modern error correction codes. What you see here is a 2D surface. The open circles are data qubits. This is where the quantum information is sitting. The closed circuits are syndrome qubits. And now we are measuring Z around the syndrome, so of 4 qubits. And by this, we get some information about an error that could occur here. And because this qubit couples to multiple syndromes, we learn something by comparing those measurements. The same for X, because Z gives you bit flip errors, X gives you phase errors. And because you're only reading out the syndrome qubits and not the data qubits, your quantum information is safe. So you're running little pieces of quantum algorithm to extract the data. And this is highly sophisticated. So you're detecting the errors as time goes on. And then in the end, you're actually correcting the output data, because if you're tracking errors also time, you learn more about where the data have occurred. And it turns out that only errors that actually cut through the whole surface, like chain F, go undetected. So they produce syndromes that are equivalent to not having an error, but smaller errors such as loops actually will be detected. So if the errors are truly random, then it will be very unlikely that an error chain actually cuts through the surface. So the larger the surface is, the less likely your errors are. Again, there's a lot of technology, there's an enormous amount of overhead. Fast forward, this is the most important type of plot in fault tolerance. So let me give you an idea what is shown. It's always important in physics that you at minimal actually explain what's on the axis. So this is the error probability in a simplified error model. It's called the depolarizing probability. So it's a probability of making an error, and we assume the errors have no structure. This is the logical error rate after error correction. So this is the error rate that comes out after running your algorithm. So you see, error correction does not make this 0, it just makes it acceptably low. And you essentially have to see how many gates do I run. If I need to run 10 to the minus 6 gates, then I probably want an error rate of 10 to the minus 7. And then if my physical error rate is 10 to the minus 5, then the green curve is good for me. Now, what you also see is that there are multiple curves. And these are there because this is different size of the error correction code. This is the code distance. And the number of qubits, physical qubits need to carry logical qubits is 2d plus 1 squared. And you see that down here, the bigger the distance is, the better the error correction probabilities. The large distance code, they even stopped simulating here. You also see that there is threshold behavior. So if your error rate is above a value that is roughly 0.3%, error correction is actually harmful. Why is that? Well, because I've shown you that error correction is a piece of quantum algorithm. So you're adding more extra things to do that could produce errors than you're actually taking out. So your quantum computer needs to be below this threshold, and it needs to be kind of far enough below. And then you need to decide how long is the algorithm that you would like to run and choose an error correction code that's large enough. It turns out if you plot this the right way, error correction down here is actually exponentially efficient. So if you're here or better there, then it's okay. You can just stay there and you do the rest of improving error correction by simply building more qubits. Now, there is an interesting demonstration in a very recent preprint from where somebody needed to make a Christmas milestone from a group at ETH, where they've chosen a 7-qubit chip and they have run a small patch of the surface code and they have repeated it. You see musical repetition signs, which I'm not sure they have made it to the official quantum algorithms canon yet. So they have measured the Z-type and X-type ancilla qubits. And they have actually in a planar chip. So the 7 qubits that I have drawn are sitting here. Here are the various input-output resonators. And this is the electron microscope picture. So the lines have been added for reading convenience. And you see they do various things. There are qubits, there are couplings, there are readout and feed lines for driving and so on. So the result is that actually the error rates really go down with more error correction. They don't quite go down as well as you expect. You would like to have the dashed line and not the other line. Sorry, this is, let's say that again. This is the loss of fidelity. Sorry, I was in the wrong plot mentally. This is the loss of fidelity from a physical qubit. And you see that the error corrected qubits are really sitting on top. So you keep more fidelity. This is specifically for sticking in the 0 state, which is the correct outcome. And then complementary 1 would be the wrong outcome. And here the same is done with plus and minus X states. So you see that there is a contrast by error correction. You also see that error correction does not completely suppress the error. Still, if I do more cycles, the error rate is going down, but it's much slower than expected. So this is a precursor that this is going to work. And this is interesting because it measures 2 in principle incompatible errors by doing this in the correct way. The bad news is that theory and simulations expected this to be even better, that the success probability is even higher than the experiment. However, this is a very simplistic model. So even just modeling the experiment more carefully would hopefully allow us to test this. This is a very complex chip. So writing down a full physical model of predictive power with enough digits after the comma is actually a formidable and partially unsolved task. So here is a good validation of error correction from a very recent experiment. Now, how does this look like in the long run? Well, this is a plot that we've made for the BSI. And this is showing, again, the physical error rate. This is the status of experiments. And this is what you would like to do. For example, the second lowest red line is RSA 2048. And because the error correction overhead has a space-time overhead, the number of qubits you need depends on how much time you're giving to you, which is 100 days or 1 day. And you see that there is still a large distance of about 10 orders of magnitude. You also see that the Google quantum supremacy experiment compared to a previous Google experiment has gone up in the number of qubits, but it really hasn't gone much to the right. And the distance is still large. So in order to make progress here, I, as a quantum computer builder, call making better quantum computers always progress. One should really go to the right. And the ion traps, so this is the superconducting platform, these are trapped ions, are on the right way. But we should probably go a bit more on the right. And then we are in the flatlands of these curves, and then the scaling curve is a bit more forgiving. So again, we really need better qubits to make consistently an error rate below 10 to the minus 3, whereas now we are kind of here. And then aggressively scaling makes sense. Is this feasible? Well, there are a number of challenges. The transmons are about 1,000 times bigger than CMOS circuits, and this is the most common superconducting qubits. But for a couple of thousand or 1 million in the chip, come on, this is 1960s CMOS, and it's complicated, but it's feasible. However, there are also peripherals. This is a nasty element called the circulator. It has roughly a 1-inch diameter. And currently, you need 2 per qubit, and you need to put them next to the chip and cool them down. I've somehow forgone the opportunity to. No, maybe I will show you a cryostat. But you've seen cryostats before, the typical steampunk-like brass-colored contraptions that house qubits. However, the hope is that you can make them a bit smaller. You can probably get rid of the boxes. And you can also hopefully soon put more qubits per circulator to make this. So this is what I would call organic progress in the field. The cryogenics, the fact that you have to cool them down, is well established and robust. This is an industry. There are even cryostat assembly lines. It gives you a number of design rules. For example, the cooling power, the feasibility to take away heat once you've produced it is really bad at low temperatures. But this can be done by essentially making sure everything is reversible at low temperatures. The supply of helium is expensible and partially hard to get, but currently not limiting. Also, for 1 million transmons, you need to break the plane, but Google has just shown that. You need to pack 10 transmons a bit more likely. And actually, as we have extrapolated a couple of years ago, building a cryostat for 1 million qubits and their periphery seems to be feasible. It would be a custom cryostat. It would be 10 times as big as the largest one that you can currently commercially purchase, which is called the Triton XL. And what is interesting is that IBM has announced last week their roadmap to 1 million qubits. Do I have another slide on this? Yes, I have another slide on this. And they have also announced that they are building the biggest dilution cryostat known to humankind in-house to do that. So they assume that, you know, this is not done by companies that specialize on these machines because there are too few customers, but they try to do this. And if you look at the IBM announcement, you see, you know, human beings inside gigantic cryostats. Also, you know, you need 2,500 rack units, but this is also coming down, the electronics stack that you need to run this. And in fact, IBM has last week outlined a roadmap that has 1,000 qubits in 3 years, and that has all the necessary infrastructure to build 1 million qubits. So this is already meant to house 1 million qubits. What is, however, interesting, and given what I've told you before, is a question we should be very well aware of, that this announcement, which I have stolen from an IBM press announcement here, has no target values for error rate and fidelity. So, and this is something which I assume, because they're very intelligent people, that they have a roadmap for, but this is the main thing that we should currently watch. Now, for 1 billion qubits, you will probably have to, which you would need for cryptanalysis in one day, you would actually have to connect 1,000 of these machines with microwaves, which is very challenging, but also there has been very recent progress. In the flagship, there is a project where 2 of these cryostats are connected by a line. Now, this is a cold microwave line, but think about this as the quantum computing version of an optical fiber. And the group at ETH, which clearly is not in this project, this is from the Walter Meissner Institute in Munich, has shown that they can transfer states between those two with an acceptable fidelity. So here the lattice, the empty boxes are what you want, and the blue lines are what you have, and clearly it's not great yet, but it's where gate-based quantum computing was roughly 10 years ago. Maybe actually also one doesn't really need this by simply making the system integration a lot more clever. Now, I've basically used up my time. Let me just essentially jump over slides for adiabatic quantum computing, which is a very different approach. It's much more physics motivated in the sense that we are not driving gates. We have a physics way called adiabatic protection to take us from the ground state of an optimization landscape that only has one minimum to the minimum of a complex ground state. And most of you are computer scientists. I don't have to tell you that there are optimization problems that are NP hard and NP complete. So if we can solve them with acceptable speed up, that would solve a lot of our problems. And what you have to look up is essentially this type of landscape, because this is energy. This is going around from here to there. This is the leading coordinate. And there is an exponential number of lines here in essentially polynomial space, which means that the average line spacing is very low. But in some cases, the lowest to the next lowest line shrink only polynomially. And this is important because this spacing, 1 over this spacing, the inverse of this spacing, tells you the speed at which you can run this. And there's a proof that this is in principle universal, and it's very popular in industry. Sorry, I have to keep time. And there's a few caveats, but there has been a recent proposal on adiabatic factoring. And this is very similar to the factoring with a NISQ quantum computer that I've shown you half an hour ago. So it essentially takes the treats factoring as an optimization problem. It shows that this can be quite efficiently embedded in hardware. However, and you always see that there's errors because the correct result here 3 times 7, here 3 times 5 is only observed with some probability, but it's acceptable probability. They also show that this is actually absolutely fast, but there is no analysis that as you go between 3 times away from 3 times 7 or 3 times 5, that you would actually have speed up in a scaling sense. Again, this is combinatorial optimization, not adiabatic, sure. So this still has to be investigated in parts experimentally. In the last 2 minutes, let me also comment that there has been a proposal on addressing lattice-based cryptography, which I think currently is believed to be quantum safe with quantum computers. So the idea here is that we need to have a shortest vector that is sitting on a certain lattice, and we can embed this in a physical platform that is based on taking physical particles and putting them into a 2D landscape that looks a bit like an egg carton, and use the fact that these can hop, and if they collide, they repel each other. This system is called the Bose-Hubbard Hamiltonian, and one thing that is special is here, you are not restricted in the number of particles to 0 and 1. You can have arbitrary numbers. And you then treat this adiabatically. So you take your Bose-Hubbard model, you change S from 1 to 0, you switch this off, you switch this on. Then you can embed your problem here, your lattice problem in this, that essentially if you reach a certain configuration, if you can reach it, you have solved the shortest vector problems. You do not really have to make this type of simulator. You can embed it into qubits with logarithmic overhead. But again, in this paper by Mintert and company, the speed up analysis is based on heuristics of extremely small systems. So there's not a clear statement about speed up you can make. Sorry, I forgot to translate this. What they speculate on is that this can be, let's stick here and I just explain this. That maybe annealing doesn't have to be so slow. Maybe you can actually, even with fast annealing, reach something. And I think the real thing to watch here is the following. This physical platform, which is from the area of quantum simulation, not of universal quantum computing, is actually currently being scaled quite aggressively. There is a very successful project that has a big node in Munich and a big node in Paris that is pushing those to the level of thousands of qubits. And if they can program it so they can really embed the shortest vector problem here properly, this is important because this is not universally programmable. So part of the work is to make the system so it embeds what you want. Then they can probably get scaling heuristics for this problem rather quickly and give us a much clearer idea about the speed up potential. So I have shown you that there are these 4 approaches to quantum computing. I have not talked too much about annealing, but there's the gate model for memory limited algorithms where the competition, where now early starters are rising, between 1500 qubits, there's a lot of engineering. And then there's fault tolerant qubit, which has an enormous overhead and which we can really start if the qubit error became an order of magnitude lower than it's now. And there's reason for optimism here, because I've been doing this now for 21 years, and in the last 21 years, the error rate has gone down by 5 orders of magnitude, which also means that for the first 10 years, we needed ways to measure it that were not even based on computing and gates, they were very physical. So you see the quantum hardware is moving fast, and so do applications. However, cryptanalysis can still only be addressed with fault-tolerant quantum algorithms, and this is still a long shot. We cannot exclude that with the activities like the one I've shown here with quantum, with the Bose-Hubbard model, that there will be some disruption, but so far nothing really convincing has shown up. I think I have slightly overgone my time, and would we see each other in person, I would probably have at some point seen that I have slightly steamrolled you, but you can now ask questions. I have not read the Mattermost. I trust Tommaso to transfer the questions to me.
Thank you, Frank. This was very, very interesting. In fact, we have a bunch of questions already. Let me ask you first something. So my understanding is that IBM, one of the predictions of IBM was to have this, by the end of 2023, this 1,000 over physical qubits. But I've also read that they are expecting to have 10 to 50 logical qubits.
Yes.
Do you think, what is your feeling? Do you think this is reasonable, too much ambitious? Do they have a disruption that we are not aware of?
So I think this is ambitious but feasible. So I don't know whether Michele Mosca is participating in the conference, but when I was in Waterloo, I learned the word non-crazy from him, and this is ambitious but not crazy. The main thing that is important, if you can run 1,000 qubits with NISQ, the main thing is important is that the readout of the syndrome qubits and the reset needs to be done reliably and quickly. So far, the reset in most cases is quite slow because it's done naturally. You wait for a natural asymmetric bit flip error to occur, which takes you all down to zeros. But there has been very good progress in doing this actively. So you measure something, and if it's 0, you're happy, and if it's 1, you use feed forward to essentially say, I have 1 now, I need to flip this qubit. So the main additional thing is that you need to, in real time, while the algorithm is running, need to take measurement data and act on them. This is difficult, but I think a lot of elements of this has been demonstrated. So I would be optimistic that at the same time, they also reach these fault tolerance demonstrations.
Okay, thank you. So ambitious, but not science fiction, let's say.
Yes, optimistic. I'm optimistic. Yes. Do I believe in it? I believe in very little.
Okay, thank you. So we have some questions from the Mattermost chat. So actually, an interesting question is, what is the, so in the layout of qubits, you're talking about arranging a 2D grid, right?
Yes.
Would it be useful to scale to the third dimension? Is it difficult? Is it attempted?
So few comments. I have concentrated on these superconducting chips because I didn't want to confuse you with the many hardware platforms that are out there. In fact, in trapped ions, people can make strings of ions with long distance connectivity. So they can cross elements in the string, which I think this is all to all. So in a way, this is like infinite dimension. Now, at some point, making longer and longer strings is coming to its end, but they now try to make arrays out of this string. If this is successful, then we can really talk about high dimensional connectivity. The beauty of the surface code is that it works in 2 plus epsilon dimensions. It's all these error correction and error syndrome detection operations are meant to be done in 2-dimensional layout. I say 2 plus epsilon because for making non-Clifford gates, for making T gates, you need to sometimes do state injection, so you have to probably make a second plane. So this, in this sense, is 2 plus epsilon, but this would work. If there was a third dimension, the error correction threshold would be a lot lower. And I think this is the reason why it's important to specifically watch ion traps where you have long-range connectivity. So here is, I've grown up with statistical mechanics in my PhD. So when we say dimension, it's always a statement about connectivity. I assume it's the same in graph theory, but let's just make this clear. It's a statement about connectivity. You could make 4D. It just means you need a lot of couplers.
Okay, thank you very much. We have other questions, but I'm afraid we are running out of time. Anyway, the Mattermost chat will remain open still for 1 week or so. So feel free to ask your questions. For all the audience, feel free to ask your questions, and maybe some of them will be addressed at a later time. So I would like to thank again our speaker.
Thank you.
And
apologies for running over time, but I'll be on the Mattermost.
No, I mean,
check in.
Okay, that's great. Thank you very much.
Yes,
so at this point, we conclude the session for a break and see you in 10 minutes for the next session. Thank you, everybody. Bye-bye.
Hi, welcome everyone to section 2.2 of PQCrypto 2020. This is the section on quantum algorithms. We will have 3 talks, each of them 4.5 to 5 minutes. And we will have all 3 talks basically without interruption, other than changing slides and presenters. And thereafter, we'll have kind of a panel for the questions. And if you have any questions you would like to ask, please put them in the Mattermost chat. And then Tommaso, who co-chairs the session with me, will read them to the speakers, and we hopefully get answers. And so without further ado, let's move to the first talk. The first talk is by Alex Helm from Ruhr University Bochum on the power of few qubits and collisions.
Hello, yes, I'm Alex, and I'm going to give you a short presentation of our paper, The Power of Few Qubits and Collisions, Subset Sum Below Grover's Bound. This is a joint work with Alexander May, who is also from Ruhr University Bochum. And our main contribution is that we construct a quantum algorithm solving the subset sum problem. So let us start with a short definition of the subset sum problem. And we are given n numbers, a1 to an, chosen uniformly at random from z2 to the n, and also a target t, also a number defined modulo 2 to the n. And we are asked to find a subset of these ai's, which sums up to the target t in z2 to the n. And the subset is here represented as a bit string e. And there exist several quantum algorithms for solving these problems, this problem. But besides Grover's algorithm, all of these algorithms uses quantum random access memory. And for the realization of QRAM, it's still not clear how much does it cost us and how many qubits we need for it. So we want to focus on quantum algorithms which work without QRAM and only with linear many qubits. And then the question is, can we beat the Grover bound with runtime complexity 2 to the n half? And we want to do this by exploiting the structure of the subset sum problem, and we want to do it via some collision search algorithm. So we first took a look at the quantum collision search algorithm by Chailloux, Naehrig, and Schrötteler from 2017. And roughly speaking, this algorithm has 2 main steps. First, there's a list construction step, where every list element is constructed via some Grover search. And then there's some amplitude amplification step, which works with some set membership oracle. And we adapt this for the subset sum case and achieve time complexity 2 to the 0.48 n. And we need classical memory 2 to the 0.24 n. And then we improve this by replacing the list construction step. And instead of Grover, we now use a purely classical algorithm. And here we use the algorithm of Schrötteler and Samir from 1981. And then we achieve time complexity 2 to the 0.43 n and needs classical memory 2 to the 0.29 n. And then we make another refinement by introducing a new parameter. And by this parameter, we can adjust the memory consumption. So we achieve the following trade-off, and we have a better look at this trade-off at the next slide in this diagram here. So on the x-axis, there's the memory exponent, and on the y-axis, the time exponent. The red line shows the imaginary Grover bound with runtime exponent n half, and the black cross shows the first result of the adapted CNS algorithm, and the blue line shows our received trade-off. And our trade-off starts at the Grover complexities with runtime exponent n half and only with polynomial amount of memory. And we go down by providing classical memory down to runtime exponent 0.43 n. And now we need also an exponential amount of classical memory. So we have to compare our results to classical trade-offs. And here we can see the dashed line shows a summary of the best classical trade-offs in their respective domain for the subset sum problem. And we can see here that our algorithm outperforms Grover search for every exponential amount of memory, and it performs best for memory complexities lower or equal to the 0.2n. And that's our main contribution. So that's from my side. Thank you very much.
Thank you very much for this presentation. So then we move right on to the second presentation. Let me just bring it on here. So the second presentation will be by Samir Hodžić from the Technical University of Denmark on quantum distinguishers for Type-3 Generalized Feistel network based on separability. Samir, it's all yours.
Thank you very much. Hello, everyone. So with respect to the recorded talk that we have, I'll just point out the central part of the paper which regards to the notion of separability. As I keep most of the original slides from the original talk here, I will just briefly go over some of them. So regarding the 3-round Feistel network, given in this picture here, so the idea of constructing the quantum distinguisher is based on concatenating two functions. Here on this slide, they are denoted with G and H. And we obtain them by querying the encryption oracle in the way so that the relation between the function G and H is given in this form here. And this is very important because this equality here actually implies that the function f is periodic in the vector 1s. So based on this observation, many other ones present in other papers, we actually introduced the notion of separability, which tries to capture the overall idea of constructing the quantum distinguishers. And it is mainly related to the placement of input blocks. So in this context, we have the notion of strong separability, which is denoted, which is related to the case when the observed branch has this form here. And here we have that the functions lambda and h are depending on the input blocks y and z. And in that context, we have that the input block x meant to be a variable is not involved in the in the input of functions lambda and h. And here it is important to know that the function lambda is a known function in the context whether it is a public function or available to querying and so on. Furthermore, we have the semi-strong separability, which has this form here. The variable y is outside of lambda, function, and z is outside of h. And the weak separability, I would say the hardest case to deal with is the case when we have this form of the observed branch, and we have that the function g depends also on y and z besides the block x plus h of pi z. The main point regarding this notion is that the semi-strong separability and strong separability allow the construction of the Simon's function in these forms here, and that is in general. Okay. But on the other hand, if we consider the type 3, which is the subject of our research in the paper, we have that 4 branch allows easy construction of the Simon's function because it satisfies the strong separability. On the other hand, we have, considering the 5 rounds, 4 branch, we have a harder case. And the main idea in this context is to consider the terms which are present in the form of the observed branch and try to actually force them to construct Simon's function in this way here. And the main problematic part is actually the second one, which actually requires that it is equal as the first function by where the input block x is just shifted with s. In this context, we have further this equality that we have to satisfy. And it actually turns out that if we have the solution for this system here containing only 2 equations, then we are actually able to construct the Simon's function f. But for this purpose, we have to employ Grover's algorithm to find these blocks gamma and beta. And of course, in this context, we also use the Simon's algorithm in order to test the periodicity in the definition of the classifier. This is actually the main part of the paper, and the rest of the presentation I will not go through it. It is just related to the application of the Simon-Grover algorithm. Thank you very much.
Thank you very much for this presentation. So as indicated, we take questions after all talks. So let's move right on to the third presentation. So Sam Jaques will speak on computing discrete logarithms with a quantum computer. And so Sam, take it away.
Hi. So in our paper, we consider the problem of estimating the actual resource requirements of Shor's algorithm to attack elliptic curve cryptography and solve the discrete log problem. And so what I think is our biggest contribution was kind of a change in philosophy compared to previous works on the same issue, where instead of considering the fewest number of qubits we could find, we thought that Shor's algorithm is probably well within the fault-tolerant regime of quantum computers, so we need to account for error correction overhead. And it's possible that having fewer T-gates or having a lower circuit depth will reduce that overhead, and the fewest number of qubits will actually be with more logical qubits, but lower amounts of other resources. And so we looked at different kinds of trade-offs and tried to improve in all of them. So mainly our improvements came from incorporating different circuit components. So we had logarithmic depth adders, more efficient Toffoli and AND gates. We used windowed point addition, and then we found a way to do better pebbling of the modular multiplication and division, and improve controlled versions of the addition circuits. And we put all this together in Q#, which is Microsoft's quantum language. And because Shor's algorithm is basically you start with a superposition, you do what is ultimately just a classical scalar multiplication of an elliptic curve point, but in superposition, and then a Fourier transform. The most expensive part is this scalar multiplication, and so we only estimated the cost of that. And this meant that there's no quantum phenomenon happening, and so we were able to test it even at cryptographic sizes. And then we also were able to produce these automated resource estimates, and the code is now publicly available at this address. And so there's an entire library of arithmetic and modular arithmetic. And so if you want to use this and build on it to estimate other circuits, this is now available. And so this is our overall results. So what this table has is 3 subtables for the different NIST standard curves of different sizes of prime moduli. And for each subtable, there's 4 rows. RNSL is the previous state-of-the-art result. And then the other 3 are from our paper and represent different trade-offs. Low W is the lowest width or fewest number of qubits. Low T is the fewest T gates, and low D is for the shortest T depth. What I think is our best result is a very large reduction in the T depth, about 12 bits, with not that much of an increase in qubits, only about 20% more. And so personally, I think that this is probably a lower qubit footprint than any of the other results, but we didn't go into the full analysis with the surface code or anything like that. This is also seems to be less than the cost of attacking RSA 2048 with Shor's algorithm. Probably what's happening there is that because RSA is classically easier to attack, it needs larger moduli to be as secure as an elliptic curve, but then that means it's just smaller integers, and so this is easier for a quantum computer to attack. You can see that the T count is lower for all of our trade-offs. Most of this, about 4 bits of this, is coming from the windowing of the point addition. 1 bit would be from the improved pebbling, and 1 to 2 bits of improvement is from better AND gates and adders. For the T depth, it's roughly the same where all the improvements come from, although you can see that the low depth row at the bottom is much lower, and this is the logarithmic depth adders, which constitute most of the arithmetic. And finally, you can see that we did manage to get the total number of logical qubits down by about 1 register, but for the other trade-offs at low T gates, we use addition circuits that have a lot of auxiliary qubits, and so they are a little bit wider than the previous result. And that's most of our results, and I look forward to answering any questions.
Thank you very much for this presentation. So we are now moving to the question session. So if you have any questions, please post them in the Mattermost chat, and then Tommaso will read the questions. So Tommaso, I hand over to you.
Thank you, Häner. Thanks to all the speakers. I would invite all of the speakers to turn on their webcam for a more interactive experience with the audience. And let's move on to the questions. So I personally have a couple of questions for the talks, but we also have a question from the Mattermost chat right now for Alex. And the question is, can your technique be used to improve generic decoding, more precisely to improve information set decoding algorithms to solve syndrome decoding? Alex, do you have any, can you comment on this?
Yeah, it's quite common that every improvement for the subset sum case can be used to have an improvement for the information set decoding. But if we want to fix the setting, so for us it means we want to work without QRAM and with only linear many qubits. This is not really feasible for the information set decoding, because the information set decoding algorithms had an inner loop and an outer loop, and if you want to be or maybe the best algorithm which works without which works with linear many qubits is this version of Bernstein, where you only use a Grover search over the outer loop. So if we then want to improve the information set decoding with our algorithm, we also have to use this Grover search on this outer loop. And then we are in the case that we need exponential many qubits, or we need QRAM, because then the list construction will be a part of the inner loop, and the outer loop, there's a Grover search. So we need this every list for every state of the in the Grover search. And so for our setting, to work without QRAM, it's not possible to use this our algorithm combined with information set decoding. But if it's not important to be in this setting, then maybe you can use it to improve information set decoding. But if you are fixed on this working without QRAM, then it's not possible, I think.
Okay, thank you, Alex. I think this is quite exhaustive. So I have actually, so let's see if there is other questions. First of all, for now, not. So then I will switch to my questions, and I have a question for Samir, actually, about the distinguisher for the generalized Feistel. So, you know, everything started with this attack from Kuwakado and Mori on the distinguisher for the 3-round Feistel. But my understanding was that a couple of years ago, it was proven that 4 rounds Feistel are actually secure as a quantum weak pseudo-random permutation. So I wanted to understand how your result let's say, compares with the known attacks on normal, like I'm talking about the standard Feistel construction. In particular, is your feeling that standard Feistel construction is more secure in general compared to the generalized Feistel construction to quantum attacks. Can you compare the two problems? Because I know that there's a lot of open questions, and maybe you can elaborate on this.
Regarding the method that we proposed, is the case is that we are observing the terms in the expression of the certain branch, the terms which are related to the input blocks, the first occurrence of every term that comes in. The trick is that if we have, let's say, generalized Feistel network with, let's say, more rounds, 4, whatever the number is, as the number of rounds is, if the number of branches is larger, then actually the occurrences of certain input blocks is happening after a little bit more rounds. So if it happens that our idea can be applied, for example, if it's just Simon, we get polynomial time. Simon Grover, something different. But the case with the classical two-branch Feistel scheme, we have that the occurrence of the two input blocks, we have only two, is happening very fast. And if we have more rounds, well, to break, let's say, 5, 6, 7, 8, or whatever the number is, it's not easy. It becomes difficult. So that is like a sort of, I will not say the trade-off, but considering the aspect of occurrences of the input blocks, it has to do something with the actually attack as well.
Okay.
So, on the other hand, regarding the classical attacks, in general, I'm not like a big professional in that field, so I cannot say like too much, but with respect to the method that we propose, that's what is happening. Well, in our paper, we just the 4-3, but the method overall can be applied to all generalized Feistel networks, and well, depending on the structure, we can have, let's say, this amount of rounds that we can apply Simon or Simon Grover and so on. So it's not the same for all schemes.
Okay. Is there any chance of extending your techniques to other constructions? So I'm thinking of, I don't know, even Mansour or even Sponge for for hash functions. Do you see any synergy that you could exploit with the internal working of these other constructions?
Even Mansour is pretty much like different from this here, because if we consider, let's say, that public permutation there and the two cases involved, then adding a public permutation there is constructing the first derivative of the function, and we know that it is periodic immediately. This happens the F construction. Well, the application of them is in context because another one more key in addition, right? But regarding the other, let's say, constructions like hash functions or, well, depends. Sponge, classical white sponge is already analyzed, and one can apply certain attacks there. But in most of the sponge constructions, which are using, let's say, either tweaks or different placement of the blocks through the rounds, it's difficult. It's pretty difficult. The main reason for that is actually when constructing the function, we want to obtain two functions in concatenation so that both of them are obtainable by querying the encryption oracle. Okay, and on top of that, we have to have the relation between the functions in the underlying concatenation. If we are not able to do that, and in most of the cases it is difficult, it's hard. So far, it seems that it is not easy to let's say, derive some different method of constructing the Simon's function. So we have the one that actually gives the first derivative, like even Mansour, and we have this one that is relying on the concatenation of two functions. And as I know, those are the only two that we have.
Okay, thank you very much. So let's move over to a question for Sam. So you did an impressive, I mean, the result is a really, I think it's pretty cool, and it's really goes in the details of analyzing the cost of quantum circuits for attacking elliptic curves. I am wondering whether you can improve let's say, the known algorithms to attack, so like Shor's applied to the discrete logarithm. How much can you parallelize this? So in the standard setting, it is known that Shor's algorithm doesn't really parallelize very well, right? So I'm wondering if there is space for improvement in this direction. Let's say you have not one quantum computer, but two quantum computers that can communicate together and working together to attack an instance of the problem. What are your thoughts on this?
So I don't really know is my main answer. This is something that I thought about, but I haven't thought it too hard or looked too hard into the literature on this. I think there's also it'd be important to distinguish. Suppose you have two quantum computers and you have some sort of limited bandwidth communication between them, versus you just have one larger quantum computer and maybe you have more qubits, but they're coherent for less time. I think there's interesting things in the second case that we sort of covered using these automated pebbling techniques where you can kind of compress the circuit even more and make it even wider if you are in this scenario. But I don't know much about the case of the two or more separate quantum computers trying to communicate. There could be interesting things on even the circuit case, like maybe you could parallelize parts of the multiplication even if Shor's algorithm as a whole doesn't parallelize well, the arithmetic might parallelize, but I don't have any specific answers of how to do that.
Okay, that's fine. We have another question for you regarding, so you already mentioned let's say the gap between attacking RSA and attacking elliptic curves on a quantum computer, and how elliptic curves seem to be even more vulnerable to quantum attacks in respect to RSA for the same classical security level. The question is, so how much does your result modify the gap, like in concrete terms, the gap between attacking these two? So can we say that elliptic curves are incredibly more vulnerable than RSA to quantum computers, or is it more or less the same situation?
I don't know. So I don't know what the gap was before. The gap now seems to be, it's maybe about 8 to 10 times easier, sort of in the product of qubits times depth, the space-time volume. So I don't know how that compares to before. And also, because we didn't do a full stack analysis, including the error correction, it's hard to compare to the RSA result, which includes that. And maybe that gap would widen a little once we account for the error correction.
Okay, I see, thank you. And a last question, maybe. Do any of your circuit optimization also, I mean, can they also be used to speed up any possible attack on super singular isogenies, elliptic curves? So because we are talking about very low level operations here, right?
Yeah, absolutely. And that was kind of the initial motivation to get into this, was to improve on circuits to do the isogenies. And in fact, the trade-off gets even better because for those attacks, they're so exponential, they often parallelize so badly. The incentive to have a shorter but much wider circuit is even greater. And so absolutely using these lower depth adders and these different techniques would work much better.
Okay, thank you. And then maybe there is, okay. I would conclude with the last question for Alex, if there's no other questions from the audience. So you're working in this, so your motivations are clear. You want to avoid this QRAM model that is kind of controversial. It's probably expensive. So how do you think that your results will have any impact on the parameters that are being considered by NIST for for evaluating the security of some of the candidates?
Okay, I would say no. But yeah, I think it's not clear now. So we have to, we can see many lattice-based schemes and also some the coding-based schemes, the McAleese. We can see most of these as a vectorial approximation version of the subset sum. But I think to have an impact on these numbers for the NIST competition, I think our results are not strong enough to have a real impact on this. But I'm not sure. So we have to further investigate this direction. So now we have this for the subset sum case, but we want to adapt this for the cryptanalytic implications in these other directions. So, for example, for short integer solution problems or decoding random linear binary codes and so on. So it's not clear, but I would say this is not really. No, I don't think it's. No, I would say we don't have an impact on these numbers.
Okay, thank you very much. So at this point, it's time to wrap up the session. I would like to thank the speaker again, and feel free to keep asking your questions on the Mattermost chat. That will also stay open for a while, I think. And so let's wrap up this session and see you on the next session. Hello, everybody. Bye-bye, everybody.
Welcome to session 2.3 of PQCrypto 2020. We will have 3 talks in the session. As before, we will have all 3 talks right after each other, no break in between. And thereafter, we'll have a combined question panel. Ruben, who co-moderates this session with me, will take care of the question session. If you have any questions, please post them in Mattermost. There should be a dedicated space for session 2.3. And so without further ado, we go right to our first presentation, which has 2 presenters, James Howe and Thomas Prest. It's on isochronous Gaussian sampling. So please take it away.
Hello. Thank you for the introduction. So this is joint work with Thomas Ricosset and Mélissa Rossi. And I am Thomas Prest, and I'm talking with James Howe. So the main motivation for this talk is a signature scheme that everyone loves. So it's Falcon. It's a lattice-based signature scheme. It's a round-tree NIST candidate, and it uses a bunch of Gaussian sampling, which is the scope of this talk. So doing Gaussian sampling over the integers, it needs to satisfy a lot of requirements. So it needs to be correct, it needs to be fast, and it needs to be isochronous. So isochronous is like a relaxation of constant time, which means that you don't want you don't want the output to depend on some secret or sensitive data. So it's not constant time, but it's the relaxation which suffices for our goals. So there has been a lot of interesting proposals in the last year for performing isochronous and fast Gaussian sampling over the integers. And the key takeaway that we want to give in this talk with our example is that basically you can propose a very simple design and it will be fast and isochronous as long as you are careful with the security arguments. And essentially the high-level strategy of our sampler is in 2 steps. So first, I recall that what we have as input is a standard deviation sigma and a center mu, and you want to sample a Gaussian sample over the integers according to the distribution of a standard deviation sigma and center mu. So the high-level strategy is that first we sample from a base sampler, which is independent of the center and of the standard deviation. And we use a cumulative distribution table in our instantiation to do that. And the second step is we will transform that into a proper sample of a pseudo-Gaussian, and we will perform rejection sampling on this pseudo-Gaussian in order to obtain a true Gaussian. And this rejection sampling is done via using a polynomial approximation for the exponential. So I'm going to very quickly describe the security proofs, the 2 security proofs that we have. So we have 1 security proof for the correctness of the sampler and 1 security proof for the isochrony. So recall that the sampler, basically it has 2 building blocks, the base sampler and the rejection sampling. And for the correctness of the base sampler and of the rejection sampling, we use classical Renyi divergence arguments. And for the correctness of the full sampler, we use a hybrid argument since the full sampler is just a simple composition of the 2 subroutines. For the isochrony, it's a bit more interesting. So the base sampler, it's straightforward to show that it's isochronous because we are using a CDT table. And for the rejection sampling, it's a polynomial. And then for the full sampler, it's more complicated because the algorithm may loop a number of times. And so we have to study the distribution of the number of loops. And so basically what we showed is that the number of iterations, it follows a geometric distribution of average, the formula on the top right of the slide. And so the numerator of this formula is independent of the secret and of the output. So that's completely fine. Transformation analysis and a Renyi divergence analysis, we managed to show that it is also independent of the inputs mu and sigma and independent of the output z. So we can conclude that the whole algorithm is isochronous.
Yeah, so for the implementation side, we can see here an asynchronous implementation of the sampler integrated into Falcon for both parameters, and we can see side-by-side versions with the non-asynchronous and asynchronous versions, and we can see like a minimal degradation in performance, so between a 13 and 18%, considering if you're using optimizations or which parameter set you use. The next contribution is a statistical test suite, which we call Saga. And we do this because their implementation failures are quite possible and quite likely. And we also see tests like this for uniform random number generators, so it makes sense to have this for Gaussians and even binomials, which we see in like the likes of Kyber as well. And our tests can look at univariate Gaussian samples, multivariate Gaussian samples, which are output from the likes of Falcon or even from fully homomorphic encryption and GPV-based signatures. And wherever possible, we also give visualizations, so graphical outputs, which show univariate or multivariate Gaussians. So that's our 5 minutes. We're happy to take any questions afterwards.
Thank you very much for this presentation. So as indicated, we'll move right to all three presentations. So the next talk would be on Rainbow by Albrecht Petzoldt. And so Albrecht, the stage is yours.
So thank you for the introduction and welcome to my talk on the efficient key generation for the Rainbow signature scheme. So as I'm sure you all know, Rainbow is the only left non-lattice signature scheme in the NIST standardization process. It offers very short signatures and has a very fast signature generation and verification process. On the downside, the public key size of the Rainbow scheme is quite large. And at least in the first round submission, the key generation process was relatively slow. And therefore, the first question we want to answer in this talk is if we can speed up the key generation process of Rainbow. On the other hand, we have the so-called cyclic Rainbow scheme, which reduces the public key size of Rainbow by up to 70% and also gives us a possible speed up of the signature verification process. However, the key generation of this scheme was very slow, and therefore the scheme was not practical. And therefore the second question is if we can speed up the key generation process of cyclic Rainbow to make it practical. So we need a few conventions. So we restrict to Rainbow schemes with 2 layers, and we restrict to homogeneous maps S, F, and T, which also gives us a homogeneous public key. And we use linear maps S and T of this special form here. And note that this doesn't weaken the security of the Rainbow scheme, because every Rainbow public key has a private key of this form. We introduce an additional intermediate map Q and look at the polynomials of F and Q as quadratic forms. The matrices F to the I and Q to the I of these quadratic forms look as shown here on this slide. And then we can compute the Rainbow key pair by performing a number of small matrix products. And how this can be done in detail is shown in my longer talk and also in the paper. So I don't want to do it here. On the other hand, we have the so-called cyclic Rainbow signature scheme, which was proposed by myself in 2010. The idea is to introduce a structured matrix into the coefficient matrix of the public key. So we choose randomly the 2 linear maps S and T, and also some part of the public key, the matrices B1, B2, and B3. And from this, we can compute the central map of Rainbow and the remaining parts of the public key. Doing this gives us a key size reduction of the Rainbow scheme by up to 70% and also gives us a possible speed up of the verification process. However, as I already said, the original key generation process included the inversion of a large matrix and therefore was impractical for the use in practice. And by our techniques, we can now show that the key generation process of cyclic Rainbow is nearly as efficient as that of the standard Rainbow scheme. So I don't want to describe how it is done in detail. So I just will present some results. So for the standard rainbow scheme, we get the following here. So you see that for the security level of 128-bit, the rainbow key pair can be computed within 2.3 milliseconds, which is relatively fast. Compared to the first round submission, we get the following picture. And for the cyclic rainbow scheme, you see that the key pair for 128-bit security can be computed within 2.58 milliseconds. So the cyclic rainbow scheme is now nearly as fast as the standard rainbow scheme, which makes cyclic rainbow to be a practical alternative to the classical rainbow scheme, with a much smaller public key and a faster verification process. Thank you.
Thank you very much for this presentation. And so we will move right on to the last presentation in this session, which is on benchmarking post-quantum crypto in TLS. And Gautam Tambada will give the talk.
Hello. So yeah, I'm going to be talking about benchmarking post-quantum cryptography in TLS, and this is joint work with Christine Paquin of Microsoft Research and Douglas Sibila of the University of Waterloo. Our main goal with this paper was basically to measure the effect of network conditions on TLS handshake completion time for various post-quantum key exchange and signature algorithms. We chose to focus on network latency and packet loss rate because these two variables can be used to model a wide variety of network conditions. This focus on the network means that, in particular, we do not consider the effect of processing power at the client or server endpoints, nor do we consider the effect of the different post-quantum algorithms on server performance. We were looking at some of the prior work that has been done by Google and Cloudflare, and the common theme in those experiments was that many clients and servers scattered across the internet would be modified to have support for post-quantum algorithms, and then they would make a number of connections, and the results would be collected accordingly. But we found ourselves asking the question, what if you don't have that sort of infrastructure? What can be done? And the answer that we came to was to do what the NetMirage and the MiniNet tools do, which is to emulate the network. Network emulation gives you much greater control over the experiment parameters because you can precisely determine the topology, the behavior of each link in the network, and the behavior of each node, whether it be a client or a server in the network. And this sort of control also means that it is much easier to link changes in the input to changes in the output. But of course, this comes with a loss in realism because it is certainly not trivial to model realistic network topologies or to model the behavior of realistic clients and servers, never mind all the devices that are often between them. And that is certainly not something we attempt to do in this paper. In this paper, we stick to a simple client-server topology. And as you can see in this graphical depiction over here, we have a number of client processors running what we call S-timer, a modified version of OpenSSL S-time, communicating with about half as many server processes running Nginx, and we emulate the link in between them. And this link is a virtual Ethernet link where we can precisely specify the delay and the packet loss experienced by each packet. And with that said, here's a sample of the results for key exchange in TLS 1.3 at the median. We basically chose ECDH with NIST P256 curve as the baseline, and we compared that against hybrid mode level 1 Kyber, Frodo, and Psych. And the first, and we chose these algorithms because of the range of trade-offs that they present. Psych, on the one hand, has the smallest public keys in ciphertext, but is relatively slow, whereas Frodo is pretty fast, but has pretty large public keys in ciphertext. And Kyber, meanwhile, has bigger public keys in ciphertext than Psych, but much smaller than ones than Frodo, and is faster than Frodo. The The second thing I want to note is that when we use TCP dump to analyze how many packets were required to make to establish handshakes, and for Frodo, a client has to send 16 IP packets in order to establish a TLS handshake with hybrid mode Frodo. Sorry, and with ECDHP 256 and Psych, a client only has to send 5 packets, whereas with Kyber, a client has to send 6 packets. And so, given that we can see the trends over here where Frodo's performance starts to degrade as the packet loss and the RTTs increase, and Psych has an expensive latency floor whose effect is only negated as the RTTs and the packet losses become very high. And Kyber performs the best of all the post-quantum algorithms. We've also chosen a similar set of authentication algorithms presenting a similar range of trade-offs, and the results for those can be found in the paper. But the main conclusions that we drew from these experiments were that on fast, reliable network links, the cost of public key cryptography dominates the median TLS establishment time, but does not substantially affect the 95th percentile establishment time, whereas on network links that are unreliable and have large packet loss rates, the communication sizes come to determine the handshake completion time, basically the amount of packets that have to be sent. And we also conducted another experiment to verify this, but as application data sizes grow, the cost of the TLS handshake diminishes in comparison to the cost of transmitting application data. And that's been my 5 minutes. Thank you.
Thank you very much. This brings us to the question session. So if you have questions, please post them in Mattermost. And then I will hand over to Ruben.
Yeah, we have 2 questions for Thomas and James on the first talk. The first question is from Peter Petzoldt. He's asking, is your algorithm suitable for embedded systems like Cortex-M?
Yeah, we skipped on that in the presentation, but there's Thomas Ponin has some implementations exactly using the sampler in Falcon. He has a paper on ePrint, and also I believe it's been put into PQ Clean and PQM4.
And if for FPGA systems or like different kind of system, there might be possibly better solutions than what we propose here.
All right, thank you. And there's another question by Daniel Alpen for you guys. He's asking about a pronunciation of some term which is getting more important in PQC, replacing the term constant time. I tried to pronounce it in a special way to leave you the choice of how to pronounce this ever in the future for now. So the term is about Isochronous. I guess you know what I'm talking about. And he asks you to now define and standardize for all the future how this term is supposed to be pronounced. So how do you pronounce it?
Well, apparently I'm the way I'm supposed to tell people how to say this because I'm English, but I think I said it wrong actually. It's Isochronous, but I might be wrong as well.
Isochronous. Okay, and so that's now that this term is supposed to be pronounced for all the future. Okay. Thank you very much. These are the 2 questions for you. Now I have one more question from Daniel Alpen on the second talk from Albrecht Petzoldt. And he asked that at the end of your talk, you briefly mentioned that cyclic rainbow has faster verification than standard rainbow. Whether that's true, and if you could elaborate on this.
Well, this is a difficult question. So there was a paper which showed that the additional structure in the cyclic rainbow scheme can indeed be used to speed up the verification process. However, when you use these vector implementations like AVX, as we did in our proposal, then we haven't found a way to use it so far.
Okay, thank you. So currently, I don't see any more questions on Mattermost. So if anybody has another question, please type quickly. Yeah, there don't seem to be any new questions coming up. Rana, do you want to finish the? Do you want to finish the session?
Yes, I mean, said the chat will remain open for the rest of the week. If there are questions that come up later, but if there are no further questions right now, I think we send people over to a coffee break or afternoon break, depending on where you're watching. And so then I would say thank you very much, and thank you very much for the speakers. So you get a limited applause. Thank you very much. Very much appreciated. And this would conclude session 2.3. Thank you very much for attending.
Thank you.
Okay, so hi everyone, welcome to session 2.4 on security proofs. So I am Olivier Blasi and I will chair the session with Thomas Prest. So we have 4 talks in this session. I'd like to remind the speakers that they have around 4 minutes 30 seconds per talk for the presentation, so try to be quick. And after the 4 presentation, we'll have a round of questions coming from the chat. So the first paper is Many a Mickle Makes a Muckle, and Ben is going to give the talk.
Thank you very much for the introduction. Hi, my name is Ben, and this is Many a Mickle Makes a Muckle, a framework for provably quantum secure hybrid key exchange, a joint work with Torben Hansen and Kenny Patterson, and my first talk given without wearing any shoes. So let's begin. So Many a Mickle Makes a Muckle is a North English / Scottish phrase, depending on who you ask, which essentially means from many a small thing comes a big thing. And this fairly accurately describes the approach that we took in our project. In our project, we combine quantum key distribution with post-quantum key encapsulation mechanisms with classical key encapsulation mechanisms to create Muckle, a hybrid key exchange protocol. This hybrid approach allows us to hedge against potential failures in the underlying QKD, perhaps due to hardware failures, or the post-quantum chems, potentially due to understudied assumptions, to achieve a quantum secure key exchange. Recall that on a high level, key exchanges are cryptographic protocols that allow 2 parties to establish shared secret keys in an authenticated manner. So this is our Muckle construction. Muckle is a multi-stage key exchange protocol, which means that the 1 round trip depicted here occurs many times in succession, executed between 2 parties, Alice and Bob. The construction of our Muckle framework is very straightforward. The backbone is the exchange of key encapsulation mechanisms. Alice begins by sending a pair of chems, public keys, to Bob, one that is post-quantum and the other that's classical. Bob straightforwardly uses the public keys to encapsulate a pair of secrets, again, one post-quantum and classical, while which Alice retrieves, by decapsulating Bob's ciphertexts. However, since these are single-use chems, we'll need to authenticate these somehow. Now, we assume that Alice and Bob already have established a pre-shared key, or PSK, between the 2. This allows us to significantly simplify our approach, and we justify this by pointing out that a QKD already requires an authenticated channel to exist between the 2 parties. In practice, this is done via use of a pre-shared key. We argue that establishing 2 such keys are in practice not significantly more expensive than establishing just a single one. Now, both Alice and Bob will use their pre-shared key to derive another key, using some secret state that we'll discuss in a second, in order to generate a MAC tag over these messages, thus authenticating the public keys and ciphertext exchange between the 2. Since Muckle is a key exchange protocol, we need to use all of these secrets to generate a symmetric key. Alice and Bob use the outputs of both chems, so this K and this QK here, as well as the keying material from the QKD, the secret state that we use to generate the MAC keys, as well as the pre-shared key and the messages to generate the next stage's secret state. So we've got this evolving state happening in each iteration of the protocol, as well as the keys that Alice and Bob will use in some arbitrary symmetric key protocol. So, summarizing up, the inclusion of the single-use post-quantum chems and the QKD allow Muckle to achieve quantum secure key indistinguishability, break down resilience in the unexpected failure of the QKD or post-quantum chem components, and forward secrecy. The PSK and the MACs of sufficient length allow Muckle to achieve quantum secure authentication, and the evolving secret state allows Muckle to achieve post-compromise security. But that's only half of our work. So in order to prove these claims, we introduced the Häner security framework for hybrid authenticated key exchange protocols, an extension of previously introduced notions of authenticated key exchange security. I won't bore you with the details here, but our approach in formalizing QKD into a security model I think is quite interesting. Specifically, we capture the QKD as a mechanism for establishing per stage ephemeral symmetric secrets, which I think is quite an elegant way to model this. In addition, the Häner protocol framework is a lot more general than Muckle, as it allows you to capture long-term asymmetric keys in both post-quantum and classical variants. Think maybe picnic public keys and RSA public keys. Finally, we prove our Muckle protocol secure in our novel Häner framework and demonstrate that Muckle achieves security against both quantum and classical attackers under certain post-quantum and classical assumptions of the underlying PRF, MAC, and CHEM components. A little fun fact, in the case where the QKD provides security, we only require post-quantum assumptions of the underlying PRF. That's not all we do. We also implement muckle in C using embed TLS for the classical cryptography and PQCrypto to instantiate our PQ chems. On the right here, you can see our muckle key schedule, which I recommend you look through the paper to find out more. We also benchmark our implementation in 2 different experimental setups, one mimicking a practical distance between 2 QKD devices, and the other one a little less practical. So that's the end of our work. Thank you very much for listening, and I look forward to your questions at the end of the session.
Okay, thank you for the presentation. So the next speaker is going to be Aldogan Singh about the collapsibility of 3 hashes. So you have the token now, and I'll let you switch the presentation.
Not switch. There we go. Thank you for the introduction. So my talk will be about the collapsibility of 3 hashes. My name is Aldo Gunsing, and this is a joint work with Bart Manning. We let h be a hash function, and the classical security definition for hash functions is the notion of collision resistance, which means that it is hard to find 2 different x and x prime that get maps to the same value under h. So for example, the hash function shown is not collision resistant as both 0, 1, 1, 0 and 0, 0 are mapped to the same value. However, it turns out that this definition is not strong enough in some quantum settings, and for this UNROLL introduced a new security definition, namely the collapsing property. In 2016, he also showed that some hash constructions like Merkle-Damgaard are collapsing. However, his proofs are very long and require a lot of quantum knowledge. So in 2018, Fair introduced a new framework for the collapsing property, which much shorter proofs and also much simpler ones. So for this, he proved some composability results of the collapsing property, which even allow for classical reasoning in proving hash constructions secure. So now we'll go over these results. So first off, we have the parallel composition, which applies G and H to some input. And he proves that this composition preserves the collapsing property. And the same he does for the nested composition, which is just a normal function composition. And also for the concurrent composition, which applies G and H independent to some values. And also finally for the disjoint union, which applies either G or H depending on the value. And for most of these, we require that both G and H are collapsing, but for the parallel composition, only one of them has to be. So Fair used these results to show that some constructions like Merkle-Damgaard and Sponge are collapsing. And here he assumes that the underlying compression function is non-invertible and collapsing. And we extend these results to some tree-based hashing modes. And we start with looking at fixed-sized trees. And we show that any fixed-sized tree hashing mode is collapsing. And this is a straightforward application of these composability properties. So this means that we actually can do like a proof by picture. So in the example, we can see that the topmost compression calls actually form a concurrent composition, which then form a nested composition with a final compression call. And this means that the whole hash function is collapsing. And we can do similar things with any fixed-sized tree. However, this does not directly work for variable-sized trees, as collisions can also happen in general. But we do prove that 2 common variants are collapsing. So the first one is based on domain separation, where message blocks and chaining values are separated. So for example, the message block may end with a 0 while chaining values end in 1. And the second one is length encoding, where the length of the message is encoded in the final compression function of the hash result, as shown in the function. But I won't show the proofs for these in this talk. that's the end of my talk. Thank you for your attention.
Okay, so thank you. So our third speaker is going to be Patrick Struck, and about encryption scheme using random records from classical to post-quantum security. So I'm going to load the presentation. It should be this one, I guess.
Yes. Well, thank you for the introduction. So this is joint work with Juliane Krämer. So in this work, we want to study the in-CPA security of public key encryption schemes against quantum adversaries. So we have a quantum adversary who outputs 2 messages, send it to a challenger. Challenger picks a random message, encrypts it, and send it back to the adversary. And then the adversary tries to distinguish which of the messages got encrypted. And we want to do this for public key encryption schemes that rely on random oracles. And this entails that the adversary now gets access to these quantum random oracles, which it can invoke on a superposition of inputs. Now, when we want to achieve this notion, we try the following approach. So we want to lift classical in-CPA security proofs, which were conducted in the random oracle model, to these post-quantum in-CPA security proofs in the quantum random oracle model. So if we look at the classical proofs in the random oracle model, they all exhibit a very similar structure. So they start with some game G0, which is the in-CPA game instantiated with the concrete encryption scheme. And then there's another game GK, which is an ideal game, where what ideal in this case means that in this game the adversary has no advantage. And then to show that the scheme is in-CPA secure, one can show that the adversary cannot distinguish this real game G0 from this ideal game where there's no advantage. To make the proof feasible, there are several more games in between, and then the overall distinguishing advantage between the real game and the ideal game is bound by the sum of each of the advantages between each pair of consecutive games. Now, this proof approach carries also over in the post-quantum setting, and the reason is that the challenge ciphertext remains classical even for quantum adversaries. But the main thing now is that each of the game hops has to be analyzed in the quantum random oracle model, while the classical proof was in the random oracle model. Now, we were not able to arbitrarily lift security for any public key encryption scheme. So instead, we define a class of encryption scheme for which we then can lift the security. So this class of encryption scheme is what we call Oracle simple encryption schemes. And this is mainly a restriction on how the encryption algorithm uses the random oracle. So here you can see how these Oracle simple schemes look like. So essentially, the encryption algorithm consists of 2 parts. In the first part, value R will be sampled at random. Then it applies some deterministic function to it to get some value X, which is then used as input to the random oracle to get some value Y. In the second step, then the public key, the message, this randomly sampled value R, and the output Y of the random oracle are input to some subroutine encrypt, which then computes the actual ciphertext. Now, main thing here is that this subroutine is independent of the random oracle, so it had no access to it. And from this, you can see that actually all the random oracle related part happens in the first part of the encryption, and it happens in this bit of a restricted way. Now, there are several schemes which fall into this class of Oracle simple schemes. So one is the code-based encryption scheme Rollo2, the lattice-based encryption scheme Lara, and also the code-based encryption scheme Bitquake. The main thing that we get for these Oracle simple schemes is that it allows us to divide the game hops into 2 different types. First, type 1, which are the ones that are independent of the random oracle, and then type 2, which are the ones that are dependent on the random oracle. So essentially, type 2 game hops are games which only differ in this used subroutine, which is independent of the random oracle. And for this, lifting the security is quite easy because the reduction only needs to be able to simulate a quantum random oracle for the adversary, and this can be done, for instance, by Qubits independent functions, as has been shown by Zentry. Now, the type 2 game hop, this would be a game where a game hop between 2 games, where in one game the value Y is the output of the random oracle, while in the other game, the value y is now sampled independent of the random oracle. And for this, due to the structure of these oracle symbol schemes, we can also show that there the classical proof holds against quantum adversaries, but as an intermediate step, we need to use the one-way to hiding lemma proposed by UNROLL. And then with this, we can prove that the encryption scheme Rollo 2 and Lara are secure against quantum adversaries in the quantum random oracle model. So this concludes my presentation. Thank you very much.
Okay, thank you for your presentation. And the final talk of the session is going to be a note on the instantiability of the quantum random oracle. And the presenter is going to be Edward Eaton.
Okay, hello. Can you hear me? Great. Hello, everyone. Yes, I'm Edward Eaton. I'm a PhD student at the University of Waterloo. Today, I'm happy to be talking to you from my living room about a paper I wrote along with Fang Song at Portland State University called A Note on the Instantiability of the Quantum Random Oracle. So Patrick's just talked a bit about the quantum random oracle model, but just to recap, the idea here is that in the random oracle model, the adversary has to interact, make calls to the random oracle that is maintained by someone managing the proof. And then in the quantum random oracle model, we want to generalize this and allow the adversary to make quantum superposition queries to the random oracle. This is done because, of course, a quantum-enabled adversary can presumably run a hash function on a quantum computer in superposition. And as we just saw, when you do a proof in the quantum random oracle model, you generally need new techniques and methods to manage the oracle and to establish that your proof techniques work, or you need sort of generic kind of proofs of classes of proofs that sort of port over to the quantum random oracle model. This, of course, is in contrast with the standard model. In the standard model, the adversary is simply given a complete description of the hash function, and we don't really concern ourselves what they do with that description. It's up to them. They might run it on a quantum computer, or they might break apart the parts of the hash function and do something interesting. And this is the model that kind of corresponds to the real world. But in practice, not all proofs happen here because, of course, getting a proof in the standard model tends to be a lot more challenging. So one thing that cryptographers have been interested in is the relationships between these models, the standard model, the QROM, and the random oracle model. And it's fairly easy to see that a proof in the standard model implies security in the quantum random oracle model, and that a proof in the quantum random oracle model implies security in the random oracle model simply by considering an adversary who only makes classical queries. But the reverse directions here are kind of what's interesting. You know, does a separation exist? And if a separation exists, what does it look like? And what can that tell us about how we need to think about these models and what we need to be careful of for considering security in the real world? So one of the first big results of this was by Kennedy, Goldreich, and Halevi in 2004, where they showed that generically a proof in the random oracle model cannot imply a proof in the standard model. And they showed this by establishing the existence of a signature scheme, which is secure in the random oracle model, but insecure when that random oracle is instantiated with any real-world hash function. But the quantum random oracle model has been around for about 10 years now, so it's kind of, it would be nice to really firmly establish its position in this hierarchy. So, you know, in the last talk, we saw a class of schemes for which random oracle model security implied quantum random oracle model security. But generically, it's now recently been shown that this isn't in the case. In a paper by Yamakawa and Jandry, the link is right there, just from this year, they established a scheme secure in the random oracle model, but insecure in the quantum random oracle model. But this talk today is about this part here, the relationship between quantum random oracle model security and standard model security. And indeed, we also established that these are two distinct models. There is a separation here. Our link to the full paper is there. So in full, our contributions are what we do is we analyze various separations that are between the random oracle model and the standard model. And we show how those same schemes can also be shown to have quantum random oracle model security, which then establishes a separation between the quantum random oracle model and the standard model. So specifically, we look at the separation from the 2004 paper by Kennedy, Goldreich, and Helm, and we show that the proof of that scheme can be elevated to the quantum random oracle model, which establishes a separation between the QROM and the standard model. We also look at some other schemes that try to show similar separations. So we look at another 2004 paper, this one from Moore, Renner, and Holenstein, and we show that, in fact, the original proof, unmodified, still works in the QROM. And lastly, both of these separations apply to signature schemes that sign very long messages. So there's a bit of a gap there in considering schemes that may only sign short messages. But we look at another paper from Kennedy, Goldreich, and Helm, and we consider signatures that are only on short messages, and we show that it's also secure in the QROM. Thank you very much, and the link to our full paper is there.
Okay. Thank you for your presentation, and thanks to all the speakers. So now, if someone has any question, please feel free to ask them on Mattermost or on the chat. So Thomas is desperately trying to get some question. So in between, yes, I invite all the speakers to activate the webcam, so I can see you.
Yes, we have plenty of time for questions, so if anyone has questions, don't hesitate to post them on the Mattermost. Okay, well, in the meanwhile, I have a question for Edward. So thanks for your nice talk. I was wondering if for encryption schemes there are similar results to what you showed, if I understand correctly, for separation results for signature schemes?
I don't entirely recall. I believe that there might be some separation results from ROM to standard model, and probably similar work could be done to show those in the QROM. But our work kind of just focused on signature schemes.
Still no question on Mattermost, so if anyone here has a question. Okay, Floyd Johnson is asking on Mattermost, are there necessary or sufficient conditions to show a scheme is oracle simple? The question is for Patrick Struck.
Could you please repeat the question? I didn't get the info.
Yes. Are there necessary or sufficient conditions to show that a scheme is oracle simple?
Yeah, it's mainly, so we have it in the papers, mainly giving this subroutine. So you can just look at the scheme, at the pseudocode of the encryption algorithm, and then you can check whether this first part, how the random oracle is involved, on which inputs that you fulfill this condition. And I mean, essentially you can show it you just look at the scheme and then you can see whether it fulfills it or not. For the schemes we analyzed, it was quite simple.
Okay, I have maybe in the meanwhile another question for Aldo. So in terms of concrete consequences, do you think that your result can make it simpler to analyze schemes that heavily rely on Merkle trees or hash trees, such as the signature scheme Sphinx, or any hash-based signature, or even signatures that, such as Picnic, that use hash trees at some point?
Yeah, it does show that those signature schemes, that they are collapsing, so that you can even use them properly on with a quantum commitment scheme.
Okay, I think there are no more questions on Mattermost. So if anyone has a further question, you can still ask them on the channel, and the channel will remain open for the whole week. And if the authors are on the channel, then they will be able to reply to your questions. Okay, so thank you very much. Thanks to all the speakers again. And okay, so yeah, this is the last session of the day. So thanks again to all the speakers.